All right, so we're going to talk about differentials today. And differentials, most of differentials today is going to be just a new notation as well, I'll say. It's kind of like back in trig. I don't know if you remember, everything was y equals for the longest time, and then all of a sudden they brought in that f of x concept. You guys remember that? And it meant the exact same thing. It was just kind of a different notation, different way to write it. Differentials are a different way to write it, and there's a couple reasons for it. When you first learned f of x, you're like, why are we doing it? This doesn't make sense to do it in this notation. Is it lighting off rockets or something?
I was just looking. A bird. Oh my god.
I thought you were a rocket.
I'm just curious if you're going to do anything productive in here today. Okay, no, it's fine. It's fine. Ignore me all day. So, differentials is kind of like a new notation, but with that new notation we have, for right now, it might be a little fuzzy on why exactly we're doing the new notation, but it's going to make a whole lot of sense later when we start doing integrals and all that fun stuff. So, so for our differentials, so far what we have is we have y equals f of x. That's just our basic, first thing we started with way back in trig. And then what we've been doing in this class is taking the derivative of this. Okay, now as far as the derivative goes, we've written it in a couple different notations. The most common notation, the way that I usually like to write it, is to put the little dash marks on it like so. And to say like y prime. Okay, that's basically saying, hey, that's my first derivative, that's the derivative of this function. Okay? That's one notation, one way to do it, and we've done that before. Okay? Another way to do this, we have y equals f of x, is to take the derivative of this, and that was writing that d over dx. I don't know if you remember that. You guys probably remember a little bit of that, right? We actually did that before. But it was d over dx. Okay, and what that says is when the y was already there, remember the y was already there, I'm taking the derivative, and that dx on the bottom meant with respect to x. Okay, which means if x is my variable, then my variables match, and I can do the derivative just like normal. Nothing crazy. Okay. Now, what differential is, and this right here would be the first derivative here. So if I still kept that little tick mark there, the y value would equal, like let's say these were not there, y equals f of x. If I take the derivative with respect to x, then I can put that little tick mark there. Okay. Now, what a differential is this. dy equals f prime of x dx. Intuitively soak that in for a second.
That's easy.
That's not too bad, right? So we okay? Now, for the things that we're going to write here, and what these stand for, they're pretty particular on what they stand for. dy over dx was actually the change in y with respect to x. So however much x was changing, y was changing. Now, change of x, we usually use that little delta x or delta y. A lot of books use that notation. But the dy here, this is saying that the y is changing a certain amount. Okay, so we have the change in y, whatever that is. That's going to equal the first derivative function, which whatever that is, multiplied by whatever the change in x is. So the change in x, which you might call like delta x, and delta x means change in x. Okay, so we're going to change in x. Now, once again, our x is like our independent variable. It's our variable that we want to agree with. So we're going to have a change in x. However much that changes, then our y is going to change the corresponding amount, whatever it happens to be. Okay. Now, there's a correlation between those, and that correlation is multiplying those together. Whatever the dx is, the change, multiplied by the derivative of the first equation. Okay. Now, dy is also thought of as delta y, or the change in y. Hey, delta.
Oh my.
She can go teach.
Yeah, we know.
You have to explain your joke. It's not in California. Oh. What are the odds? Okay, now let me just say one thing here. This dy right here, dy and delta y are actually just a slight bit different. They actually say that dy is approximate to delta y, which is kind of a weird notation there, but it's so close that it's not going to matter. And I'll show you graphically what that means and how that's going to work in a second. We're going to go a little bit into theoretical here first before we actually get like real good numbers. So dy is actually going to be really close to delta y. Now, it's not going to be exactly the same. The dy is actually how much the y is actually changing. Delta y is the change in y, which is kind of hard to see. But let me just graphically explain what the heck is going on here. Let's say I have some graph that goes like that. And I pick some x value. Let's say I pick some x value at this point right here. And then I pick another x value out here. Now the second x value is going to have some delta x change. I want some distance there, right? So this distance right here is going to be my delta x. Okay, whatever I decide to change my x. And usually that delta x is pretty small, right? I just want to change it just a little bit. Okay. This x value now is going to be my x plus delta x. It's going to be my x plus delta x. Okay, now as far as my y values go, this value right here is f of x, right? That's our function notation, kind of weird. This value right here is f of x plus delta x. Okay, that's not too bad. Okay, now our dy is actually an approximate, and our delta x is the exact value that it actually changed, okay? So if I were to build, like, let's say I were to build, like, little dotted lines through here, like a little t-chart right here. This height right here is f of x. Okay, that's how much the height actually changed. That's whatever this is off the ground. This entire big height right here is going to be f of x plus delta x. Okay, now the big thing that we have, you okay? No? This point right here, this height right here, is this value, f of x plus delta x, which I just rewrote right there. Okay, so that's that entire height right there. Okay? Now,
just something weird, like, it just happens to be that.
what do you mean?
Why is it f? Why is that?
The f of some value is our y value, right? If I say f of x, that's really y, right?
Yeah.
So if I plug in an x value, x plus delta x, into my function, right, that's my y value for that. So that tells me how high off the ground it is. That tells me how high off the ground it is. So that's what I'm looking for. I'm just doing it. It's just function notation. Sorry.
Okay.
Yeah. Now the difference here, this little f of x right here, that's going to be your y value. That's your f of x. This little change right here, however big this little height is right here, that little guy right there, that's like your margin of error right there. Now what we're doing is we're taking some value right here, and we're drawing a tangent line on that value. Now if I draw my tangent line right here, let's say I draw my tangent line, this value that's right here is a little bit different than that value, and that's why they're approximate. That's why they're close to each other. Now, it's so close that it's really not going to matter, especially when my margin of error, especially when my difference is going to be super, super tiny, okay? But what we're looking for is we're looking for actually this height right here. Now, this height is actually going to be f of x plus delta x. That's the total height. Take away this little guy right here. So f of x plus delta x. Take away f of x. That's going to be whatever our delta y is. Okay, so that's our actual change in y. That's literally how much the y has changed. Now, this is a lot more work than what we want to have to do. We want to do it a simpler way. Okay, and the simpler way is to look at the derivative function. And the derivative function says if I take dy, which is close to the change in y, that's f prime of x multiplied by dx. Now, f prime of x multiplied by dx is actually going to be this little piece right here. It's kind of small, but it's just that little piece right there. Now, these two pieces are going to be so close to each other that that's why these are going to be approximate or really close to each other. This is way simpler to use, and so that's why we usually use this version instead of this. So we're going to try to avoid using this at all costs if we can. Okay, at least that's our goal. Okay. All right, now, that was a lot of theory and a lot of, whoa, geez Louise, what's going on? I'm going to show you a couple problems that are going to make this just a little bit easier, and then hopefully we're going to be good. Okay. Let's approximate the square root of 25.3. Okay, we'll go to simpler numbers if we can. Okay, so we want to approximate this, so your first step would be, grab a calculator and see exactly what it is, right? Blah, blah, blah. No, we're going to try to do some of this stuff without a calculator. Now, notice what it's pretty close to, right? It's pretty close to what number? 25, right? It's pretty obvious. It's like, oh yeah, we got the square root of 25. I know what that is, right? So you should be able to at least ballpark about what the answer is going to be, okay? So what I want to do is I want to approximate the square root of 25.3, and I want to use that by using the square root function. Now, my function value, my function f of x is going to equal the square root of x. That's the function that I'm talking about, okay? Now, if I thought about what the graph looked like, right, on square root of x, the function of that, the graph of that function is one of these guys like that, right? You guys are all okay with that? Now, if I'm picking the value 25.3, right, 25.3, I go out to 25.3, and I get my exact value right there. Let's say I went to 25. Okay, 25 is going to be just to the left of that, just short of that, right? But if I draw a tangent line to that, how far apart are those values going to be? Pretty small, pretty insignificant, right? So that's my goal, is to find that little tiny change right there, to find out exactly how much this has actually changed across my entire value. Okay? So what I'm going to do is I'm going to look at the square root of 25, and I want to look at 0.3 being my difference, being my change in x. Okay? I'm going right here to 25, and I'm going here to 25.3. That means that my delta x is 0.3. Okay? I'm changing my x value 0.3. I'm just going a little bit off of that. Okay? So that's my x value. So what I want to do is I want to find dy, which is going to be the actual value here. I'm going to try to approximate this. dy equals f prime of x times dx. Okay, this right here, this is always going to be kind of your starter for today. We always want to start with that. That's the formal differential equation is this guy right here. Okay, and that came from taking the derivative of the y and the dy. You guys all get it. Okay. So from this guy, I just got to plug and chug through this formula if I can. I'm looking for dy. I'm looking for how much that y actually changed. Okay, I'm looking for how much the y changed versus how much my x changed. So what I'm going to do is I'm going to take dy equals f prime of x. Okay, so what I want to do is I want to look at what's the f prime of x function? What's the derivative function if I call that f of x? 1 over 2 square root of x. Yep, 1 over 2 square root of x. Good. 1 over 2 square root of x. Multiplied by dx. Are we kind of okay with that? Okay, now what I'm looking for is dy. I'm looking for how much this is actually going to change. So I've got dy equals, now the x value that I picked, and I picked a nice one, right? What was my original x value that I picked? 25, because that's a good one, right? 25 is my original x value. So I'm going to plug that in. I'm going to go 1 over 2 times 25 multiplied by dx. Okay, and dx is my change in x, how much I decided to change it, which is how big? 0.3. Okay, so I'm going to multiply this by 0.3. Yeah.
So why do you use the 25 and not the 25.3?
Because the 25 is my close approximation to it. That's the good number that I like to start with, and then I changed it by 0.3 as my approximation. So I'm trying to get close. I've tried to do this without a calculator if I can. Back in the olden days, they didn't have calculators, and the calculus geeks evaluated them like this, which is crazy. At least they get a ballpark. You know? All right, cool. So to simplify this isn't too bad as far as simplification goes, right? I've got dy equals 1 over 2 times the square root of 25 is 10, multiplied by 0.3, which is 3/10. And so this gives me 3 over 100. Okay, so 3 over 100 is how much off that y value actually is. Okay, so if I want to approximate the square root of 25.3, what's the square root of 25? 5. Plus the approximation, the difference that it was, 3 over 100. Okay. So 5 plus 3 over 100 should approximate square root of 25.3 form. Because 5 is the square root of 25, that's like my original function value, right? What I calculated right here with the dy is how much y changed from my original x value. What I looked for, I found that little 0.3 over 100, that's how off this value is, this height right here. It's kind of hard to see, but that's that height difference right there. So I want the original height, which is 5. That got me up to here. And then I want that little extra right there just to bump it up just to where it needs to be. Okay? So I have 5 plus 3 over 100. And then 3 over 100, if I just add that in there, what's that going to give me? It's 5.03 roughly, right? Now what happens if I take, I guess I can show you guys this. What happens if I take the square root of 25.3? 5.0299 stuff, right? So approximately they're close. Now, there's 2 different things I did. This one right here would actually be considered like your delta x. This would be the exact value, okay? That's kind of like your delta x. This is your dy, which is a slightly different, but hey, those are pretty close approximate-wise, right? Now, the closer and closer I make that value, the better my approximation is going to be. Let's say I did 26, right? Let's say I did the square root of 26. Let's see how off that would be. Okay, and once again, I'm just doing approximations. Let's say I did square root of 26. Now, the square root of 26, 26 is not a very nice number, right? That's kind of gross. Right? But square root of 25, I know. Square root of 25 is good. So what I want to do is I want to think of this as, once again, the square root function. My x value here is going to be 25, and my delta x is going to equal 1. X plus delta x, that should equal my value that I actually want, which is 26. Okay, so when I plug this into my little function here, my dy, this is just my approximation for this. This is going to be f prime of x dx. We're always starting out with that generic differential. This is a generic differential equation. Okay, so dy is going to equal f prime, which we already got, 1 over 2 square root of x multiplied by dx. And so when I plug that stuff in, my 1 over, I still want to plug in a good number that I know. I'm trying to do this without a calculator if I can. So my dy is going to equal 1 over 2 square root of 25 multiplied by dx, which is going to be a 1 on this guy.
Well, will you always have 1 over 2 square root of x?
That's the derivative of this guy. It's always going to be the derivative of whatever the function is. So this one happened to be, the derivative of this guy happened to be 1 over 2 square root of x. Because that's the derivative of square root of x. I'll do a different one so it's a different function. But for a square root, it's always going to be that. Yeah, for a square root. So, all right, cool. So let's go ahead and simplify this. So this gives me 1 over 10. So 1/10. Right? Are we okay with that? Okay, so my dy, the change in the y value, the change in the height, right? We're changing the height, is 5 plus this little change in the height, which is 1 over 10. So it should be 5 plus 1 over 10. Okay, which is, let's see what that is. 5 plus 1 divided by 10. I didn't have to put that on my calculator. Awesome. And it's 5.09. So it's actually still pretty close, right? Now, let's say you pick the number like 28. The bigger this gets, the further off it's going to be. The closer you get, then the closer it's going to be to your approximation. And that's just because if I have my graph like this, as I do a tangent line to this point right here, as I drift away further and further, this gap gets bigger and bigger. So my change in y is going to spread. Okay? I'm basically approximating a value on a curve with a tangent line, which is kind of a weird thing to do. So, yeah.
Okay, so you're trying to find the derivative of y equal to the derivative of x or something? You said something earlier,
No.
and like when you pointed at the calculator, you're like, this is the derivative of x, this is dy. And
Yes, okay, right. There's two different things. There's two different guys here, right? This guy's an exact value. Would you agree?
Yeah.
Okay, so that's the exact change in y. Okay, so that's going to be delta x for that. Okay, so that's going to be how much, or that's going to be whatever your x value is. Okay, or y value is. Sorry. This one's going to be your change, and this one's going to be your dy, which is how far off from the actual curve it's going to be. So we got a little bit of difference there.
Wait, is that the change in the delta y or delta x?
Y.
Okay.
Yep.
Because you said
Did I
delta
say
x
that?
before.
Oh, I didn't mean to say that. Yeah. No, delta x on this one was 0.3, and delta x on this one was 1. Because it was how far off of what I wanted to actually get. Okay, that was the delta. So, all right, let's do one that's a little harder.
Coral.
Ready for hard stuff, right? All right, let's do. All right, let's say we have a cube. Okay, so let's say we have a cube, and we got sides are going to be 12 on this cube, and I want to find we have a margin of error. They're going to say with an error, margin of error of 0.03 inches. So a pretty small margin of error. If you were to go, to some kind of manufacturing plant, and they have, I don't know if you have ever seen watch one of those shows, how it's made or things like that. They have all that machinery that's doing it, and they have these margins of errors for whether or not something can actually be, a product that they can sell. So if I have a cube that's supposed to be 12 by 12 by 12. Then I want to have it, to be about that size. Now, it could be a little bigger, a little smaller. It has a little bit of flex, a little bit of play. But I want it to be within a certain range so I'm not wasting material and so my product's consistent and blah, 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 blah. So let's say I have a cube of 12 inches, and my margin of error is going to be 0.03 inches. What I want to do is find out how much that's actually going to affect the volume. Okay, so I want to find out how much it's going to affect the volume, and then relatively, for big picture, what's that going to do for me? Okay, so first thing you want to do, what we're going to find, we're going to write this down, and they have fancy words. Find the propagated error.
Propagated.
I'm a horrible speller, so I'm pretty sure I got that right. What?
You just said, I'm a horrible speller, so I'm pretty sure I got that right. Whatever.
I said, but I'm pretty sure I got that right.
Oh.
Okay, so there's two different errors I want to find. First off, I want to find out how much the volume is actually changing, right? My lengths are going to change 0.03 inches. I have a little bit of play in there. Now, as those guys change, my volume of that guy is going to change as well. So I want to find out exactly how much that volume is changing, and I want to find out relatively, is that a big deal? You know, do I have is it changing like 30%, or is it just like, you know, up a 0.5% or so? Is it realistic for me? Okay. So I want to first start out with a basic function. First off, I'm talking about volume. Okay. So as far as my volume is concerned, it's a cube, right? So what's the volume of a cube? Length times width outside, but it's a cube. X cubed. Okay, sure. X cubed sounds pretty good. Now let's say I want to write a differential equation for that guy. Okay, well that means take the derivative of that, which would be like d over dx, right? So d over dx. And we want a d over dx this side, so we got to take the derivative of this side. Okay? So we want d over dx, take the derivative of this side. So my dv is going to equal 3x squared dx. We okay with that? So that's my differential equation right there.
Would dx be the point of 3?
Say that again.
Would dx be point of 3?
Dx would be the 0.03. Perfect. That's how much your x values are changing. That's exactly right. Now, what's the x value for this cube? 12. Okay, that's how much I want it to be, right? I want this to be 12. So for my dv is going to be a 12 squared, multiplied by dx. Dx is how much that x value is actually changing. So the error in my x value is 0.03 inches. So I'm going to multiply this by 0.03. And I'll multiply all that together. That's going to be my dv value, which is going to be how much the volume is actually changing. Once again, it's approximate. It's not exact, but it's pretty darn close, as you saw in all the other things that we're doing. Okay? So multiply all that stuff together, and we get... Did you guys get it already?
12.96.
12.96? Okay. Okay, now that's the volume. So this is going to be what? Inches cubed for this? So we're changing 12.96 cubic inches, which maybe sounds like a lot, maybe sounds like a little. I'm not really sure, right? It depends on how big the actual thing is going to be, right? Well, what I just found right here, 12.96, they call that the propagated error, which is the error in the actual volume, okay? So that's the first part, finding the propagated error, which is finding the change in V, right? How much is that volume changing off of that? Now, what's the actual volume of the cube? What do I want the volume to be? 12 cubed, right? I want it to be 12 cubed. That'd be the actual volume of it, okay? So I just cubed 12, so what's the volume?
1,728.
Okay, 1728. So that's inches cubed. And so what I want to know is that a big number compared to this? Maybe. What percent of that is that? How do I figure that out?
12.96 divided by
How do you put it on your calculator? You just divide it. Yep, you just take dV. If you take dV, which is how much the volume is changing, over what the actual volume is, that'll give you your relative error. Okay, so just divide those out. So 12.96, divide that by 1728, and I get 0.1.
You have 3.
Oh, yeah, shoot, awesome. 0.0075 is what I'm getting. 0.0075, which is 0.75%. So do you think that's a big deal or not? It depends. You know, less than 1%, that seems pretty fair, right? That doesn't seem like an inordinate amount of waste. Okay, so that means that I can have this relative error of 0.03 and be pretty happy. I'm getting less than a 1% difference in my thing. Now, as you raise this number up right here, you might be throwing less product out, you know, because if it doesn't fit in there, you have to send it back to the melter and have it remelted and, you know, do it all again. So, you know, you have to figure out if that's going to be worth your time and what your percentage breakthrough is going to be. But less than 1%, I think that'd be pretty fair. So, anyways, we're getting the general idea. Yeah.
Well, wait, isn't the 12.96 like that's the total volume of what we thought it was?
No, that's the total difference in volume. That's the difference. So if the highest this volume could be would be 1728 plus the 12.96. That'd be the actual maximum of the volume that it would be if it fit my margin of error.
Right.
Okay. Does that make sense?
Yeah.
Okay. Kind of like the square root, right? This right here was like that square root of 25 plus this was whatever our error piece was, right? So that's the same thing of what we're doing. Okay. So does that make sense? Not too bad there, I hope. The big thing is getting to a differential equation, which is really just taking the derivative and moving a dx on the other side. That's all you really, notation-wise, that's all you have to do. Yeah.
Well, I think something's throwing me off. Like, it says with an error of 0.03 inches,
Uh-huh.
and we have an error of 0.75%. Like, what is
In the volume.
what does this mean?
What does this mean? This means this. This means this. Let me show. Let's say I have a cube. Let me draw it. Okay, so there's my cube, and I want these sides to be 12 and 12 and 12, right? Now, if I'm manufacturing these cubes, they're not all going to be perfectly 12, right? They might be a little bit off. That means I've got a little bit of margin for error as far as my cube goes. I could have this be a 12.03 and this be 12.03. Okay, I have a little room, a little fudge room, right? What I'm saying is if those sides are that much off, how much is my volume off?
Oh,
Does that make sense?
yeah. And
Okay.
so our volume is 0.75% off.
Big. It's 0.75% off of what we wanted. Exactly.
Okay.
Perfect. Relative to how much we wanted, this was that much bigger. Okay, or that much off, basically. Okay. All right. Cool. We could do another, but I feel like we're gonna. What time do we have? 10:20. Oh, we're good on time. Yeah. What's up?
Which one's the propagated error and then?
Propagated error is the 12.96. How much actual volume was different, right? The relative error is percentage-wise. How much is that?
Okay, sorry.
Okay. So, all right, cool. I think I'm going to cut you guys loose so you guys have actually time today to work and ask me questions if you need to. So, 240. And it's the last block day.
It's kind of depressing. Thank you.
Not really.
That means summer's coming. Yeah, it's kind of like that good bad. Like, it's good because